Okay, so I guess I hoped that we had gotten rid of Francesca Bartolucci, as Lorenzo has recently taught me how to pronounce her name. But no, she pops back in and she will give us a talk on phase retrieval of band-limited functions for the wavelet transform. Please, Francesca.
Thank you very much, and good afternoon to everybody, and thank you for attending. Yes, today I will present a joint work with Rima Alefari and Matthias Wellershoff about the phase retrieval problem for the wavelet transform. I will start explaining the meaning of all these words, so phase retrieval, band-limited function, and wavelet transform. So the first question, of course, is what is phase retrieval? So phase retrieval refers to a general class of problems in which one seeks to recover an unknown function from phaseless measurements. In general, phase retrieval problems can be formalized in a Banach setting, but since I will work on L2, for simplicity, I will formalize phase retrieval in Hilbert setting. So I denote by H a Hilbert space that for me will be the space where the signal that I study live. And I denote in this way the scalar product of this Hilbert space H. And I suppose that the measurements we can get can be written in terms of a family of function in the Hilbert space H, which is called also system of measurements. And I suppose that the measurements can be written as the modulus of the scalar product of the unknown function f with the scalar product with this family of function psi of I. So the question in phase retrieval is if it is possible to recover f, so to reconstruct f, starting from these phaseless measurements. So the first question to ask is if this reconstruction is unique. So is it true that if f and g have the same measurement, then f and g are equal? And this in general is not true. Indeed, we can observe that, for example, if f and g are equal up to multiplication by a constant with modulus 1, then since the scalar, the inner product is linear on the first entry, then it is easy to verify that the measurements of f and g are equal everywhere, but f and g are not equal. So the better we can hope in a phase retrieval problem is to reconstruct f up to global phase. So we cannot hope to do better. We cannot hope to reconstruct uniquely f. So the right question is not if we can reconstruct uniquely a function f, but the right question is, can we reconstruct a function f up to global phase, which means up to multiplication by a constant with modulus 1. And in this way, I denote a function up to global phase with these square parentheses. So, and we can formalize the phase retrieval problem also introducing a nonlinear operator as follows. So we denote by the H tilde. So in this way, the Hilbert space H where we identify functions that are equal up to global phase. And we denote by A of psi, so it depends on the system of measurements, the operator which maps a function f into the set of the measurements. So we see that this operator is well defined because if two functions are equal up to global phase, they have the same measurements for the above computation. So this operator is well defined, and question here is equivalent to ask if this operator is injective. So, and we need to define the operator on this equivalence, so on this equivalent space with this relation, because otherwise this operator is never injective. Today, I'm interested in investigating the phase retrieval problem when this family of functions, so the system of measurements, is of a special kind, so is obtained fixing a function psi and constructing this family of functions by dilating and translating the fixed function. So precisely, we fix a function psi and we construct the family of functions, so the system of measurements, by translating and dilating the function psi. So I denote by psi b or a the function translated by b and dilated by a. So for example, here we have a Gaussian wavelet, and we see different versions of dilations and translations of the function, the fixed Gaussian wavelet here in blue. And in this case, the scalar product of a function in L2 with this family of functions is a well-known object in harmonic analysis. Indeed, it is the wavelet transform. So the wavelet transform of a function in L2 associated to a function, a window psi in L1, is the collection of the scalar products of f with the family of function obtained by translating and dilating the fixed psi here. So in this case, the scalar products are well known and are the wavelet transform of f. And in this context, usually, so the window psi is chosen such that the Fourier transform of psi in 0 is equal to 0. And in such a case, we call psi a wavelet. This condition is equivalent to require that this integral is equal to 0. And the name wavelet refers to the fact that if a function psi satisfies this condition, then the function is forced to have some oscillations. So the functions cannot be, for example, a bump, cannot be a Gaussian, because otherwise this integral is positive. In order to be negative, it has to be some oscillation. For example, here you see that has an oscillation. Now we have the definition of the wavelet transform, and it is clear what does it mean, what we can imagine what is the wavelet phase retrieval problem. Because we ask if we know not these scalar products themselves, but the modulus of these scalar products, and we ask if we can recover f. So the question that we want to answer is the following. So we know the modulus of the wavelet transform of f with respect to a wavelet of a wavelet psi. And we want to understand if we can recover uniquely up to a global phase the function f. So the modulus, here we have the scalogram, so when which is the modulus of the wavelet transform of f at different time here of different translation b and at different scales a on the y-axis. So I just wanted to show a scalogram to show how it looks like. In this case, this is the scalogram with respect to the Morley wavelet of the following signal here. And the Morley wavelet, I will define this wavelet later because it will play a crucial role in our work. So the question is to understand when, in this case, the operator, the phase retrieval operator is injective. So I define as before this operator in this special case. So I fix a closed subspace of L2 and I identify in this space the functions that are equal up to a global phase. And as before, this operator maps a function f up to a global phase in the set of its measurements, so in the modulus of its wavelet transform. And the question that we want to answer is, for which choices of the closed subspace M and for which choices of the wavelet psi this operator is injective, which means for which choices of the closed subspace M and for which choices of psi I can answer to a positive question here. So I can recover up to a global phase F starting from its scalogram. So before presenting the space that we choose and also the class of wavelets that we choose to prove the injectivity of this operator, I want to recall what was already done before us. So I want to recall a previous result by MaLGa and Walsburger that they prove in 2015. So MaLGa and Walsburger, they considered a special class of wavelets, the so-called Cauchy wavelets, that are defined as follows. So Cauchy wavelets, here P is a natural number, and a Cauchy wavelet is Fourier transform, as you see, is supported just on the interval 0 plus infinity. This is the characteristic function of the interval 0 plus infinity. It decays faster than any power at infinity, at plus infinity, and it goes to 0 with infinitesimal order p at 0. So, and they prove that if two functions in L2 have the same wavelet transform in modulus with respect to a Cauchy wavelet, then they can conclude not that the signals themselves are equal up to global phase, but they can conclude that the positive frequencies, so the analytic part of the signals are equal up to global phase. So I briefly recall the definition of analytic representation. So when I have a signal in L2, the analytic representation that I denote by F plus is the function defined as follows. So is the function whose Fourier transform is equal up to multiplication by 2, but is equal to the Fourier transform of F for positive frequencies, so on the interval 0 plus infinity, and is the analytic representation has no negative frequencies. So the Fourier transform is 0 on the interval minus infinity 0. So the analytic representation simply is the function which contains just the positive frequencies of the function f. And what they are able to prove is that if they consider a Cauchy wavelet, so a wavelet of this form, then if two functions f and g in L2 are such that their wavelet transform is equal in modulus everywhere, then they can conclude that the analytic part of f and g are equal up to global phase. In precisely, they prove more because they prove that it is enough to know that the wavelet transform of f and g are equal in modulus for every b in R, but they need just to know for two scales, just two scales. So they prove more, but for simplicity, I decided to state the theorem in this form. So a corollary, a simple corollary of this result is that if we restrict the attention to analytic signals, which are the functions in L2, which have just positive frequencies, so such that the Fourier transform is supported on 0 plus infinity, then it is easy to observe that up to multiplication by 2, an analytic signal is equal to its analytic representation. So by the previous theorem, we can conclude that if two analytic signals are such that the wavelet transform is equal in modulus everywhere, then they are equal up to global phase. which is equivalent to say that the operator here is injective if we consider psi a Cauchy wavelet, and if we restrict L2, if we restrict from L2 to the space of analytic signals. So we found, so they found first pair when this operator is injective. So when psi is a Cauchy wavelet, and for when we restrict to the space of analytic signals. So a natural question now is to ask if, because real valued, when we have a signal in L2 which is real valued, then it is enough to know the analytic part of the signal in order to recover the signal itself. And then it is natural to ask if it is also true for up to global phase, in the sense that if I know that f and g are real valued functions in L2, and if we know that the analytic part of f and g are equal up to global phase, is it true that they are equal up to global phase? But unfortunately, the answer is no. And so in order to reconstruct up to global phase from the modulus of the wavelet transform, real valued signals, we need to find so we need to find another class of wavelets, and we need to restrict to another space. Indeed, so I just want to recall these results on real valued functions, so that I told before. So when I have a function in L2 which is real valued, it is well known that the negative frequencies and the positive frequencies of the function are related. And this formula simply states that, for example, when we have a real valued wavelet whose Fourier transform is real valued, for example, the Poisson wavelet, this formula just means that the Fourier transform is an even function. So it is clear that if the Fourier transform is an even function, when we know the Fourier transform on the interval 0 plus infinity, it is enough to recover also the negative frequencies, and so to recover the signal itself, because the Fourier transform is an isomorphism from L2 into L2. So what is true is that real valued signals are uniquely determined by their positive frequencies, so by their analytic part, but unfortunately is not true in general that if the analytic part, so if the positive frequencies of two real valued functions, f and g, are equal up to global phase, it is not true that the signals themselves, so the functions themselves, are equal up to global phase. And for this reason, we can state a first result, which is a negative result in the sense that we found pairs of wavelets and a closed subspace of L2 for which this operator is never injective. Indeed, so if we take a progressive wavelet, so if we choose psi a progressive wavelet, which means just that psi is an analytic function, so that the wavelet psi has just positive frequencies, so the Fourier transform is supported on the interval 0 plus infinity. Then if we restrict also to the L2 function that are real valued, this operator is not injective. And the proof is very simple, is divided in two steps. The first one is to observe that if a function is, if the wavelet is an analytic function, then and we have that f and g are such that their analytic parts are equal up to global phase, then the wavelet transform of f and g in modulus are equal. And this follows directly by the fact that if a function is in this Hardy space, so is analytic function, then also translations and dilation of this function are still in this space. So this space is invariant under translations and dilations. And since the wavelet transform is the scalar product of a function f, for example, with this family, the scalar product, so the wavelet transform, just depend on the positive frequencies of f and g. So if the positive frequencies are equal up to global phase, we have that the modulus of the wavelet transform is equal. But as we told before, we are able to reconstruct functions, real valued, that are equal up to global phase for the positive frequencies, but they are not equal up to global phase in general. And so we are able to reconstruct functions that are not equal up to global phase, but such that their wavelet transform is equal in modulus. So this is a negative result, and now we want to state a positive result. So to find a subspace of L2 and a family of wavelets for which this operator is instead injective. And first, I want to introduce the space of signals that we are interested in, which is the Periwinner space. So the Periwinner space, I recall, is the space of functions in L2 whose Fourier transform is compactly supported. And the space of functions is particularly nice because the Periwinner theorem holds, which states that a function is in the Periwinner space if and only if it can be extended to an entire function on the complex plane of exponential type. So a function is in the Periwinner space if and only if there exists an entire function such that of exponential type, which means that it satisfies the following condition, such that when I restrict this entire function to the real line is equal to f. And in what follows, when I consider a function in the Periwinner space, I don't consider the class of function, but I consider the continuous representative of the class. And another very important property for our goals is the following lemma, which states that if two functions are band limited and real valued, and if they are equal in modulus everywhere, then we can conclude that they are equal up to a sign. And this is not true in general, but in this case it's true, and this is fundamental for our main theorem. So now we have this space, which is the space where we take signals, so where the signals we consider live. And now we want to introduce the class of wavelets that we will consider in the main theorem. So the class of wavelets that we want to consider are wavelets with finite vanishing moments. So I recall the definition. So we say that a function in L1 has n vanishing moments if the integral of psi times the power of x from 0 to n, these integrals are 0. So for example, if a function in L1 has 0 vanishing moments, this means just is equivalent to say that the Fourier transform in 0 is equal to 0. And more in general, a function in L1 has n vanishing moments if and only if the Fourier transform, so the Fourier transform at 0 goes to 0 faster than n. And we see that this is a generalization of the previous remark, because here a function psi has 0 vanishing moments if and only if the limit of the Fourier transform of psi is 0, but the Fourier transform is continuous, and so this exactly means that the Fourier transform in 0 is equal to 0. So we are interested in wavelets such that there exists a natural number such that this limit is not 0. So because if the limits for every n is 0, we say that psi has infinitely vanishing moments. And if there exists n such that this limit is different from 0, we say that psi has finite vanishing moments. So we consider, we are interested in function in L1 psi such that this limit, so there exists a natural number L such that this limit is finite, so is different from 0, which means that the infinitesimal order of the Fourier transform of psi at 0 is equal to L, is finite and is equal to L. And we are interested in this class of wavelets because they have a good approximation properties, as this proposition states. So these approximation properties, well, they were already known well. What we did was to consider, so to verify these approximation properties in the case when we consider band limited functions. So in the case when f is a band limited function, so it is true that also the wavelet transform as a function of the first variable, so as a function of the translation variable, is also a band limited function for every scale A. And it is true that the wavelet transform of f converge to up to multiplication by a power here of the scale, converge to the L derivative of f. And this convergence is pointwisely, so everywhere. And here L is exactly the order of the infinitesimal order of the Fourier transform of psi at 0. So, and this proposition, so the behavior of these wavelets is exactly at the core of the proof of our main theorem, which is that I now state. So the main result states that if we consider a wavelet with a finite number of vanishing moments, so in this here I suppose that the infinitesimal order of the Fourier transform of psi at 0 is equal to a finite L. Then if I have two functions, two band limited functions, f and g, which are real valued, and such that the wavelet transform of f and g are equal in modulus everywhere, then I can conclude that f and g are equal up to a sign. Equivalently, this means that if I consider this operator that we introduced at the beginning, and with psi a function with a finite number of vanishing moments, and if I restrict the attention to the space of Periwinner to the Periwinner space of functions, real valued functions, then this operator is injective. So, and the next step is to ask if it is necessary to know.
Excuse me, Francesca, can I ask you a question?
Sure.
In this statement, you don't require the band limitation to be uniform. Is not PW of omega?
PW, yes, PW of omega.
Okay,
yes.
Okay.
Sure.
Okay.
Yeah,
Okay.
sorry.
Okay.
Yeah. Yes, sure. Sorry. And so the next step is to ask if it is necessary to know the wavelet transform, that the modulus of the wavelet transform of f and g are equal everywhere, or it is enough to know that it is equal on a sequence. And the fact that it is enough to know, so to conclude the same, it is enough to know that they are equal on a sequence, follows by the sampling theorem that holds for Periwinner spaces. So it is well known that if we have a function which is band limited, then it is enough to know the function on a sequence which depends on the support of the Fourier transform of f omega here in order to recover f everywhere. So this theorem allows to conclude that it is enough to, so with the same, so we consider again a wavelet with vanishing moment, so it's the same hypothesis as before, and we consider a sequence of scales which goes to 0. Then we can conclude that if f and g are band-limited functions, real-valued, and whose Fourier transform in modulus is equal on this sequence. So for the translation, we just need to know the wavelet transform on the sequence which depends on the support of the Fourier transform of f and g, here omega. And it is enough to know the scale on a sequence which goes to 0. Then we can also conclude that f and g are equal up to a sign. So this theorem states that it is enough to know that the wavelet transform in modulus is equal, not everywhere, but it is enough on a sequence of this form. And at the end, to finish my talk, I would like to show an example of a wavelet which satisfies the hypothesis that we require here. An example is the so-called Morley wavelet. The Morley wavelet was introduced by Grossman and Morley in the 80s, and it is at the origin of the wavelet theory history. And one of the most important thing I want to underline is that this wavelet is complex valued. So you see here the complex, so the imaginary part of psi dotted and the real part non-dotted here. And it is important because since we consider real valued signals, if also the wavelet psi is real valued, when we consider the modulus of the wavelet transform, we don't lose a phase information, but we just lose a sign information. So the problem is less interesting. So if we have an example of a complex valued wavelet, so that we can recover from the modulus of the wavelet transform, the functions, where we don't have just a loss in the sign, but in the phase, it is more interesting. So for this reason, I wanted to show an example of a complex valued wavelet. So, and it is interesting to look at the expression of the Fourier transform of the Morley wavelet, because we see that the Morley wavelet is, so xi0 is any real number. And we see that the Morley wavelet is a translated Gaussian. So for example, here you see a translation, we translate a Gaussian by 5, is centered in 5. And we add to this Gaussian a corrective term, and this corrective term is added in order to have 0 mean. So this corrective term is added in order to make psi a wavelet. So in order to have that the Fourier transform of 0 in 0 equal to 0. And from this figure here is not clear because the value here are very small, but the behavior of the Morley wavelet, the Fourier transform of the Morley wavelet is this one. So in 0, it is 0, and then we have here an oscillation, and there it goes to 0 asymptotically at -infinity. So this is the behavior, if we look. And it is easy to prove that the infinitesimal order at 0 of the Fourier transform of the Morley wavelet is 1. So this limit is different from 0. And so by our theorem, we can conclude that when we have, every time we have two band-limited functions, real valued f and g, such that the wavelet transform in modulus with respect to the Morley wavelet is equal everywhere, or on a sequence that we of the kind we saw before, then we can conclude that f and g are equal up to a sign. So, and as I told before, here we don't have just a sign, we don't have just a loss of sign, but a loss of phase, because f and g are real valued, but in this case, psi is complex valued. So when we add the modulus, we have a loss, we lost the phase information, not just sign information. So, but and we can recover f up to a sign. So with this example, I have finished my talk, and thank you very much for your attention. And if you are interested in more details, this is the preprint on archive. And thank you very much again.
Thank you very much to you. So, are there questions or remarks from the audience?
I have a question.
Yeah.
Sorry.
Matteo, please.
Okay. So, if I well understood, you proved this injectivity result for signals belonging to this Periwinner space. So I didn't understand if maybe you have some guess if this injectivity would hold on a bigger space, or you think that this result is sharp in some sense?
For the moment, we don't know if it holds also for a bigger space. I don't think that is sharp.
Okay, thanks.
Yeah, but I don't know. At the moment, I don't know. So it's something that I'm investigating at the moment. For which spaces and for which classes of wavelets also, because there are wavelets that are not included in the class that I'm considering now. And so I would like to understand more for sure.
Okay, thanks.
Can I ask a question?
Yes.
So the first thing is, I haven't understood why you said to Filippo that you have to fix omega in the statement.
No, I thought about it. It's not necessary, because if you pick two functions, then you find an omega that fits both.
Okay. Yeah, I see. Yeah.
And the second thing is, can you give us an intuition on why you only need low AK in the discrete case?
Yeah.
Let me see. Yeah.
Just on a sequence.
Yeah, but on a fixed sequence, arbitrary small.
Yeah. The fact is because the proof works as follows. So you know that so if I know that the wavelet transform in modulus is equal on a sequence of scales that goes to 0 at 0, I can conclude that by the approximations properties here, I can conclude that the limit when the scale goes to 0, I can conclude that the modulus of the wavelet transform of f converge to the L derivative of f at b, and the same the modulus of the wavelet transform of g converge to the L derivative of g. So since I use this approximation result, and I need just to know that they are equal on a subsequence.
I understand.
Because the first step is to prove that from the modulus, from the fact I know that the modulus of the wavelet are equal, and I want to shift the information on so the shift information that I know that the derivative of f and g are equal in modulus. And I use this approximation property, and so I just need to know the information on a subsequence. So
Okay.
this is the reason.
Thank you.
Yeah. So.
Are there other questions? In fact, I was curious to know, how do you then conclude from having information about the modulus of the derivatives to say that the functions coincide up the face? That seems to be the hard part.
Yeah, because the fact is that when I have f and g, so I know that they are equal in modulus, the derivative. So I know that they are also band-limited functions. So if I have a band-limited function, if I take the derivative, is also a band-limited function and is also real valued. And so I can conclude by this theorem here, this lemma, that they are equal up to a sign.
Okay.
The derivatives. So for example, the L derivative of f is equal up to a sign to the L derivative of g.
Yes.
Okay. Then I write, because I know that f and g, so the f and g are in the Periwinner space, so they are analytic functions. So I can write the Taylor polynomials of both f and g. But if I know that they are the derivative of the L derivative of f and g are equal up to a sign, this means that the Taylor polynomial of f minus g is equal to 0. So it's finite, it's a finite polynomial.
But, okay, I thought you had information about the derivatives only up to a certain order. Only up to a certain order. All of them. Okay.
No, I have that from a certain order. So I have that the derivative of f and g are equal the L derivative. So I know just that the L derivative of f and g. But if I know that the L derivative of f and g are equal, I know that all the other derivatives are, so the later derivatives, the L plus 1 and etc. are equal.
Okay.
So I can write the Taylor polynomial of f minus g, or f plus g, so up to f, so f minus g, f plus g. And what happens is that this is a finite polynomial.
Yeah, Filippo is not teaching analysis 1 anymore, so he's...
No, I'm lost.
You see?
He's doing analysis 2 now, so he needs time. You need to be patient. Yeah.
So I don't know if you, so if I have, so it's a finite polynomial, but then if this polynomial is not 0, I have a contradiction, because I have on one side f minus g or f plus g, which is a function in L2, and on the right side I have a polynomial. So I have a contradiction, so this polynomial has to be 0, and so the function has to be, also the other derivatives have to be equal up to global phase, and so the functions have to be equal up to global phase.
Okay, clear. Are there other questions or remarks? I don't see raised hands, so thank you very much, Francesca, and it was a pleasure.
Thank you to you.
Thank you.
Thank you.